Hey everybody, in this video we're going to take a look at how a substance's intermolecular forces can help to explain the types of properties, specifically the physical properties that that substance will have. In this case, we're looking at HCl compared to Cl2 and trying to explain why would HCl have a lower boiling point. The same series of steps that I'm going to walk through in this video, you can see them listed here on the left, would help you answer really any similar question about any set of substances and whatever the physical property is that you might be trying to explain. Before we get started, it's worth mentioning that when you're talking about intermolecular forces and how strong they are, there's an order to this that we usually accept and go with. And I'll keep this relatively short because we could throw others on this list, but I'll just use the most common ones. That would be hydrogen bonds are usually the strongest, right? So if you're ranking them by strength, that's typically given as the strongest type of IMF. Just regular dipole-dipoles you might put as, beneath that. H-bonds are a type of dipole-dipole, but a really strong type. And then at the way bottom are these forces called London dispersion forces. And LDFs are really what we're talking about here today, because while we put them at the bottom because they are generally the weakest, they don't have to be the weakest. That's just like usually the weakest. So when you have to guess, and that's the key, if you have to guess about the strength of a London dispersion force, you would probably guess, yes, they are weaker than dipole-dipoles and H-bonds because they usually are. But what makes this question, and a lot of questions that you might get in a chemistry class, unique is that we don't really have to guess about the strengths of the intermolecular forces that exist within each of these substances. And I don't have to guess because in this scenario, the property that we're comparing is given to me. I already know from the beginning that chlorine gas has the higher boiling point. I'm going to label that just because that's going to be a key detail in the comparison we're about to make. And that's going to be important because if I know in advance which substance has the higher boiling point, I already know which substance is going to have the stronger attractive forces between the particles, and it's going to be chlorine. When I teach this to my students, I like to tell them that the property never lies, and that's a good way to think about this thing, right? If I already know in advance and I'm not making a guess at just what is usual or normal, I already know that whatever intermolecular forces exist between chlorine molecules, they must be stronger than whatever intermolecular forces exist between HCl's based on that property. So keep it in mind as we go through these steps. I'm going to start with the same first thing we always do when we're analyzing molecules and their the physical properties they're going to have, and that is the Lewis structure and the shape. Now, luckily, that's fast and easy here because these are both diatomic elements. They're both linear. There's not really too much to consider. If I start checking the next thing in line from that, which is the electronegativity difference and any potential polarity, I don't really even need to look up the electronegativities to see that two chlorines attached is going to have a difference of 0. There is going to be no difference at all. I think chlorine's value is around a 3, right? So if you did look it up, you would just end up doing 3 minus 3, which is of course 0. If I'm right about 3, let's just assume that I am, then of course here we're going to have an electronegativity difference that's a lot greater. All of that just to tell me something I already spotted just based on the shapes of these linear molecules. HCl is polar. There is a net dipole, whereas Cl2, because it's two of the same exact atom, is non-polar. There is no net dipole. And that matters, of course, because the polarities of the molecules will tell you the types of intermolecular forces each thing will have. Polar things are going to experience dipole-dipole forces. So if you get one HCl next to another HCl, they're going to stick together with dipole-dipoles. There's going to be LDFs also, because all substances, at least all atoms that have an electron cloud, are going to have LDFs. Over here with Cl2, because it is nonpolar, LDFs are the only force that molecule would experience. Now that I know the types of intermolecular forces that are going to be existing here, I can start to consider which of them might be stronger and why. For LDFs, that's dependent on two factors. I've underlined them in green: how polarizable and how long are the chains. Now, these molecules are not chains. They're just, simple diatomic two-atom molecules. So I'll clarify. Chain length is not going to be a factor here. There will be a very slight difference in polarizability because the Cl2 is made of 2 chlorines, whereas HCl only has 1 chlorine. And the atom it replaces it with is a hydrogen with a super teeny tiny electron cloud. So that means HCl is going to be less polarizable and Cl2 is going to be more polarizable. And all of that work is really built up to this point because what I have to be able to explain is the strengths of those intermolecular forces, which is stronger, which is weaker, and why, because that's going to eventually allow me to explain this property that we're taking a look at. Now, this is also the key detail of this video, so make sure you're paying attention here. I'm going to do it 2 ways, and the first way is going to be the wrong way, just to make the point. If I had to make a guess, I would say that because HCl has dipole-dipole forces and Cl2 doesn't, it has only LDFs, I would say that the dipole-dipole forces in HCl are stronger and the LDFs between Cl2 molecules are weaker. And that guess is based on what is usually true about London dispersion forces, which is that they are the weakest type of intermolecular force. But here, though, I want to go back to something I started this video with, which is I don't have to make a guess. I don't have to go with the usual strength ranking for LDFs because I was told the property from the beginning and the property never lies. Remember that Cl2 has the higher boiling point. Its intermolecular forces must be stronger no matter what they are. In this case, those LDFs, the only force that chlorine molecules have, must be stronger than any intermolecular forces that HCl has. So I'm going to get rid of my original prediction because I don't have to make a prediction. I know that the intermolecular forces between Cl2 molecules must be stronger. Those forces are only LDFs, right? It does not have dipole-dipole forces, so there's no comparison that needs to be made there at all. And that means over here, the forces between HCl molecules must be weaker. If you're looking for a reason why the LDFs between HCl are weaker, why are the dipole-dipoles weaker and these LDFs stronger, we've already figured it out back when we analyzed polarizability and chain length. Because the HCl has a hydrogen with a super teeny tiny electron cloud, it is less polarizable, and 2 chlorines bonded together must be more polarizable enough to actually give Cl2 stronger LDFs than both the dipole-dipoles between HCl and its London dispersion forces. Those stronger LDFs between chlorine molecules, of course, mean that more energy is required to separate the molecules and break those stronger LDFs. This leads to Cl2 having the higher boiling point and the opposite being true for HCl. It's going to mean less energy is required to separate HCl molecules from each other and break those weaker dipole-dipoles and weaker LDFs. That also wraps it up for this video. Thanks a lot for watching.